3, 4, 5. Let's just wait for maybe 2 more minutes and we should start anyway at that time. Okay, so let's start anyway. In today's course, we will see how the 3D works. In previous lecture, we have drawn this cube, right? This is a cube. We make it by just providing the vertices for all the cube, and we give each side with different color. But we cannot find it. It doesn't look like the cube, right? Because we haven't provided any perspective, any projections, or there's no transformation here. That's what we will do here. We will add some of this transformation. So in order to do it, Let's see. First, we need to have our GRM library because we want to make some animation. Let's see how we add it. Let's make it rotate first. Then we will look at the theory and mathematics behind it. So first we add this library. I mean, how to add this library? I have just added to send you the configuration, right? But there's some simple way. I mean, just find the folder which have this. I mean, if you download the GRM, it might have some folders called GRM inside of it. Find that folder. I mean, to make sure you find the right folder, just open it. And if you open the GRM folder, you can see this file. Then that's a folder. I mean, you can copy all the folder to your project, just like the soil. When we did the soil, we did the same thing for the GRM, and you can use it. That's the simplest way to do the setup for the GRM. So the simplest way is you just download the GRM and put it here. Just copy the GRM file and put it here in your project. I mean, that's for Visual Studio. If you're using Visual Studio, the simplest way is to download the GRM file. I mean, please use the right folder. The right folder is the one which, if you open the GRM, you can see the grm.hpp file. Then that's the right one. Okay. So once you add it, you can include this header file. And there should be no error. If you see some errors here, it means, okay, you didn't include the right header file. And to make it work, and to make it transform, let's see here. We should first create something called transform. We use GRM namespace, and we use this type mat4. So this is a 4x4 matrix. Now we want to add some rotation. How we add it? We just use this rotation. From the GRM. So for GRM, the rotation is this. Transform equals to GRM rotation transform. It rotates itself. And we want it to rotate radians 20 degrees. And it rotates along this axis. Then in order to do this, we know the rotation just works on the shaders, right? It works on the vertex shader. So we need to make it work. The way we make it work is to apply the transformation here. So something like we import this transformation for transform and transform times. Just make it work on the points. So the only thing is we need to set value for transform and make it here. So how we do this? We do it here. So first we find the transform's location and then set value. The only difference is the function we use to set. Unlike the textures, we just gr uniform. I think that's that time we use gr uniform 1i, but now we use different. It's called gr uniform matrix for FV, and we get location from our shader program transform and we assigning one matrix to it. So this is one matrix. Fourth, and finally is GRM value pointer is transform. We just did this. So we find the transform's location, the variable, and assign the transform to it. So now we have to rotate. Okay, so we can run the code and see if we have made something wrong. Yes, we rotated, right? See, we rotate the matrix. So now we can see more faces. We can make it keep rotating just by adding some time here. So this is so we can add the gr get time, fw get time. So add one time function and cut it to float because this only accepts a float number. So this is more like the data conversion. Data type conversion. This is double, and we convert to float, and float times float. Now, if we run the code, you can see this cube is rotating. Right. Now it rotates. Okay, so once you have this, now let's look at the theory behind it. Let's see why it works and what are the mathematics behind it. We need to see how not only rotation, but something like scaling, translation, and maybe some other things like sharings, some other types of transformation. Okay, so let's not talk about code. Let's go to some slides first. Then we will go back to implement more transformation. Okay, so every kind of transformation can be described as a matrix times a vector. So like this, we have a matrix and the vector. We multiply them, we get a new vector. So vector can be seen as a points. So this is the coordinates. X, Y, Z. If for three-dimensional, then we can treat the vector as coordinates. And here the matrix is just transformation. Think of this is just like what we did. We times the transformation with we multiply transformation with the points, a position, and we get a new position, a sign. So this is transformation. But the question is, what those numbers are related to these different kinds of transformation? We want to know the meaning of this number. And we know this from the linear algebra, right? We know all these things. But we haven't known what are these means. We want to know what are these means, okay? Now we have the chance. Let's go here. Let's see the first kind of transformation, the scaling. So scaling is if these entries are zero, just in the diagonal part, those entries are not zero, and those numbers can be treated as the scaling. So for example, if scale as 0.5, 0.5, so we have this matrix, right? We time this 0.5, 0.5 to our points. We find, okay, the final points are just 0.5x, 0.5y. So it's half of the original points. That's what these figures shows, okay? So the original points times with, so we multiply this matrix with these points. We get new points. This is scaling. Okay, so next. This is called sharing. We didn't use it too often, but we should know what this means and what are those entries mean. So if the diagonal is 1, they're fixed and to be 1. What are those two mean? I mean, if we apply this one with some value, it just shares these things. It's sharing these things. according to the x-axis. That's for this. If you change the value here, share along this axis, the y-axis. So we can formalize this by just set this variable to be s, and s is a tangent function of phi, and this angle is just this angle. Okay. So next, rotation. This rotation is what we just did, right? But what's the mathematics behind it? We treat rotation as kind of matrix multiplication as well. But how we prove it? First, we represent the points using the polar coordinate system. So the points have been described as this polar coordinate system, right? The length together with angle, right? So rotating A along the z-axis to B with angle phi, and we can write in this way. So in the new points, we can write this new polar coordinate system. We expand it. This is a high school mathematics. Okay, we expand it, and then we replace xa, ya to r cosine alpha and r sine alpha. So we get this. We can rearrange this to get a transformation matrix, which looks like this. So this is the transformation matrix. Rotating along the z-axis. So here we have x and y, but z-axis is almost like rotating along the original point or 0 point. So this is rotation, and we group this rotation matrix and get this. Now we have seen so many transformations, right? But they're just very simple transformation. What if we want some complex transformation? More complicated than this? We can group them. We can do the composition of this transformation. We can apply the scale first and the rotation, and then maybe on some other transformation. So for example, if we apply scale first and then rotate, we can write this transformation like this. And we know for the linear algebra, this matrix multiplication, we can group these two first. So multiply R with S, so multiply rotation with scaling, we get the transformation matrix. And now the transformation is much more complex. So this is way how we get complex transformation. But the thing is, the order does matter. If we apply scale first, then rotate, we can get this kind of shape. But if we apply rotation first and then scaling, we end up with this figure. So you see, these two figures are different. It is because we apply different orders of transformation. Next, let's extend the transformation to 3D, because those are 2D transformation. If we extend to 3D, we get this. Okay, so this is the scaling. We just have 3 different axes. Rotation, we rotate across 3 different axes. So this rotate along Z axis, rotate along X, and rotate along Y axis. Notice the difference, and this is shading. We do not require you to remember all these mathematical things, but you should know what are those means, okay? So once later on, if you do some research about the graphics, or if you're making some games and you want to use this, you can quickly go back and see what's going on. Okay, and then we can do the arbitrary 3D rotation. We ignore this, just show you how we did it. We rotate first, and this is like we do the coordinate system. We apply the coordinate system transformation. I mean, we align a new coordinate system to our original world coordinate system, and rotate, and then just do the coordinate transformation back. So why we do this? Because we are trying to rotate a arbitrary vector. We can create a coordinate system along this vector. And we can make this vector along with the z-axis by doing this transformation. Then we rotate the z-axis is just like rotating along the arbitrary vector. Then next we rotate back. So this is the formula to rotate along any arbitrary axis. There is one thing we should mention, is the normal. Surface normal is not guaranteed to be perpendicular to the tangent plane. Let's look at this shape. After some kind of rotation, some kind of transformation, I think this is more like the shearing, the surface normal changed. I mean, in horizontal part, the surface normal, I mean the new normal is the same with the original one, but on vertical direction, it's different. So how to find the new normal from the original normal? I mean, we know we apply some transformation, but what about the normal? How the normal is related? Let's go back here and see. This is a way to prove how we get the new normal. You can simply remember the results. This is transformation. We get the inverse and then do the transpose. Then multiply with the original normal. We get a new normal. And this is the proof. We might need this quite a lot in every kind of lighting system. Okay, because lighting is about how the light is act along different kind of normals. Okay, so this is normal function. Now we have seen this some kind of transformation, but there's one transformation we haven't touched, which is called translation. For translation, it's not just this, right? It's more like we add some constant to our points. But we don't have this in our matrix, 2x2 matrix. This is in 2D. Because for 2x2 matrix, everything should be related to x or y. That's why we have something called a homogeneous coordinate. So you remember, in our vertex shader, if we want to represent points, we use vector 4 rather than vector 3. And we tell the last entry should be 1. By doing this, we can add this constant. Using this homogeneous, this new matrix, 3x3 matrix for 2D, we can write this. So, for this 3x3 matrix, we multiply with the homogeneous coordinate system. We can get this transformation together with this translation. And the final coordinate is still 1. So we get new coordinate. This is the standard way to do the transformation in computer graphics. I mean, both in academic area and industrial area. Okay, we always use this vector 4, homogeneous coordinate. And this transformation is also called the Eiffel transformation, because this is linear. So let's see a composition. We can do the translation first, and scale and translate again. So this kind of operation is to simulate some kind of transformation we do every day. For me, I just did it several times. I open this window and I moved here, resize it, right? So this is more like the transformation we did. So the whole transformation, we can just write everything here. So first we translate it here, right? So this is first time we translate here. Then scale, the scale is here. And then translate is here. Just pay attention to the order. The first transformation we applied, rightmost it is. Okay, so this is the order. And we multiply them together. This matrix is a complex transformation which did the whole thing and transform this shape to this shape. Now we can also get the inverse of transformation matrix just by inverse every one of them. And don't forget the order also need to be reversed. This is the theory behind the transformation and all the mathematics here. I mean, if you need it in the later, if you're doing some research, you might need it in the future time. This is a place you can refer to. Okay. So let's have a short break, because we start a little bit late. So let's have a rest until 2:40, and then we will continue the course. Okay. Okay, so let's go back to the course. Now we will implement all this transformation here. Now let's add the let's first add some scaling, because scaling is simple. Scaling is simple. We can just do transform GRM scale 1 for transform. And we know this scaling is just we just need to set 3 values for the diagonal, right? We set this 5.5. And we say now if you remember, this shape has been scaled down, so it's smaller than the previous look. And we can also add some translation. There's also GRM 3, 5. So we rotate it a little bit left. Just this, just one value one time. So we rotate a little, translate a little bit. I think this is right. So actually, it's rotating along this way. Let's make it quick, so you will see. But first, let's make it 30 degree, and then make this to be 1. You will see what I mean. You see, it's rotating, but not on a fixed point. It rotates on here. I mean, we can also change the orders. I mean, if we change the orders to make the translation before the rotation, actually it means that we rotate first and then translate. Then it looks different. You see, so it's rotating here. It's not like the previous look, right? So it means the order does matter. Here we might need to make it 0.5. So it looks better. So we can see the whole shape. It's not rotating along the original point. It just rotates here. Now you can try different value to see how it looks. I mean, we might have different kind of speed, because for me, because it might be different. If you're using different kind of laptop, the speed might be different, but you can cater this number to make sure you have almost the same performance. Next, let's add some keys. We want to add some keyboard. I mean, if we can press some key to close the window, then it's much better than this time. Every time we want to close the window, we should just close it using our mouse. Right? We want to add some keyboards. Not just only for the ESC key to close the window, we also want to do something later using this keyboard. So the best way we do it is we keep a local variable to record all this kind of key. So what we do here is we create a new function. Oh, sorry, my laptop is stuck. Okay, anyway. So we create some function called void. Key callback. function. We want to use the grfw library to help us for this key. This function will be used as a parameter for GFW function. Because it will be used as a parameter, those data type is fixed. You can't change them. If you change them, you will not be able to read this function. And we keep a local record for the keys. We try to keep a record about all the keys we pressed. If we release, we also delete it. By using this, we need to set the key pullback function. It should be somewhere here. For this window, we set the key callback function. Next, let's implement this function. We copy this and paste here. Don't copy this semicolon, okay? We implement the key callback. So this is just if statement. If the key equals to GFW, I mean if we press the key escape, and the action, because we need to know what the action we're doing. And we press, then we should close the window. Set window should close. But we keep a record for all the keys. So if we test the key is a valid key, we keep a record. First, we check the action. If it's pressed, we keep it. Else, if action is released, make it false. So we don't keep it again. Now let's see if we can press the escape to close the window. If we press escape, yeah, the window is closed. And here, just do remember, we have this is compare, and this is assigning. Okay, don't mix use them. If you mix use them, you might find it's different. It's totally not what we want. Especially here, if you mistaken use assign instead of compare, the window just closes all the time. Okay, so now we have seen how the 3D works. We have seen all this 3D transformation. We have seen the theory and the implementation. Actually, the implementation is simple, and the theory is not that difficult. I mean, if you do remember something about the linear algebra, you'll find it's quite simple. And we won't continue the next part, because next part we will learn something about the view transformation, which is another subject, because we try to simulate the camera. Right. Here now we have all the 3D object, but if you still look at this cube, you'll find it's not a cube at all. It's a rectangle, some kind of shape, but not a cube. That's because we don't apply the camera projection yet. So for the camera projection, it's all about the view transform. We will see how the view transform makes the object more obvious, I mean more correct. Because that part is how we actually simulate the camera. Right? Now we have the shape, we can have the color, we can have the texture, but we didn't simulate the camera. View transformation is all about simulate the camera. And we will see the theory and the implementation next week. And there's one more thing. Next week, I need to check the homework, okay? Because we assign another homework. The changing texture, okay? If you still remember, the texture is keep changing. So read to texture and makes changing from one to another, just like what we did for two colors, rectangle changing the color. You might need to find some information or some tutorial online, but it's okay, but you should be able to implement that. And we will check it on next Tuesday. We will also have a Tencent meeting or World meeting. So if you finish the job, show me the work. It might take 10 or 20 minutes to check the homework. Then we will talk about view transform. Yeah, and that's all for today's lecture. Make the code works. If you need me to scroll down or scroll up, just let me know. And I will be here. Okay, so that's all for today. Just see you next week.